I hope this will work as well. Okay. Can you see my screen? I don't hear you. I don't know. You can unmute yourself so that I can hear you.
Yes, yes.
Yes, yes. Okay, very good. So we're still doing special relativity. So let's see, what were we doing? So last time we discussed tensors. Right. So I basically define a tensor as a multilinear mapping from a collection of K dual vectors and L vectors into R. So a KL tensor, right, which we wrote as T nu 1 nu K as upper indices, nu 1 nu L as lower indices, right, is a multilinear map from a collection of K dual vectors and L vectors to R. That's a definition. Okay. And with that, that makes our life much, much easier. You may not see it right now, but that's the way it is. Now, okay, we spoke about the transformation laws of tensors. We said that each component transforms like a vector if it's an upper component, like a dual vector if it's a lower component. And the classical example is, of course, the metric tensor. And I said that this metric tensor, again, I view it as a multilinear mapping from two vectors into R. So eta, which operates on two vectors V and W, gives a number, right? Just V dot W, which is a real number, right? And because of the importance of this operation, then this specific operation is called the inner product. Right? The norm of a vector, of course, is the operation of the eta on the vector twice. So eta VV is just V squared, just eta mu nu V mu V nu, or if you want, it's just V mu V mu. Or the way I wrote it, it's better to be written V nu. V nu. Okay, now I specify that the vectors can be, the norm of the vectors can be either smaller than 0, equal to 0, or greater than 0, in which case the names of the vectors are time-like, light-like, or null, or space-like. Right, so eta mu nu, v nu, v nu. Smaller than 0, this is a time-like. Equal to 0, it's a null, or light-like. Greater than 0, it is a space-like.
Yeah, Saf, I have a question regarding it.
Yes, please.
So I know that, of course, photons have, traveling in the speed of light always, and etc. But can one define like formally for velocity, I don't know, and everything for a photon? Because as you said, the norm is 0 and the tau is 0, so you're in a problem.
You're very right. We're actually going to say some words about that today. We're not in a problem. It's just photons follow light-like vectors. The other way of thinking of it, which you're slightly ahead of me because this will be the first thing we're going to do after the recap. But let me ask you the following question, and I'll answer it in a few minutes. How long does it take a photon from the sun to reach Earth? Do you know?
8 minutes.
8 minutes, very good. And how long does it take a photon from the sun to reach Earth from a point of view of the photon?
No time.
That's true. Oh, what happened? That's true. 0. Right. From a if you could have a if you could sit with the photon, right, from a photon's perspective, right, it takes 0 time from the minute it is being emitted to the minute it's being interacting with you and disappears, or interacting with anything. That's the true meaning of it. Okay, we'll discuss that shortly.
Okay, thanks.
Okay, now we said a few things that you can do with tensors. You can use the metric tensor and the inverse metric tensor, right? Eta mu nu. The inverse metric, right? Eta mu nu is defined such as eta mu nu. Eta mu rho is just delta mu rho, right? So the inverse metric. You can use the metric and the inverse metric to raise and lower indices, right? Remember, when you do that, you always operate on one index and it does not change its location, right? So if you have T, alpha, beta, gamma, delta, right, multiplied by eta, mu, gamma, that's going to be equal to T, alpha, beta, mu, delta. And what really happens here, right, is that we have a summation over the dummy index, gamma. Right? Do not forget that. Okay? Good. That's why we can use the metric and the inverse to lower and raise indices, especially in vectors, right? So V mu, just eta mu nu, V nu. But again, there is a summation here, don't forget it. Right. After we worked quite hard with all these definitions, then the physics, we got out pretty straightforwardly without really the need to do much, right? We said that if we want to describe the location of an object, right, as opposed to Newtonian mechanics that we specify the spatial coordinates x, y, z as a function of time, right? We cannot do that because time is a coordinate now. So we looked at what's called a world line. So the common way to visualize it is to look at 2 dimensions, which is often the way we work with, and the y-axis it will be CT, the x-axis it will be all the spatial locations, essentially. And then we can draw a world line as simply a line which always propagates in time. By the way, in this notation, what would the world line of a photon look like?
A 45 degrees line.
Exactly, right? So a photon will always move in a 45 degrees. Right? Because it can move in each direction, but only in 45 degrees. By the way, and if you look at this region here, you know how we call it?
The light cone.
This is called the light cone. Very good. Because if I'm right here, everything within the light cone is within reach if I travel at speeds which are less than the speed of light. Namely, it is physically reachable. In other words, it will be causally connected. Something that happens here can, in principle, affect any event that might be happening within the light cone. right? But it may not affect something here, because to reach from this point A to point B here, one must be able to travel at speed which is faster than the speed of light. So no information can be converted from point A to point B, right? Now in quantum field theory, you'll find out that there are some mathematical problems in there, but there are some sophisticated mathematical ways of overcoming that in order to conserve what's called conserving causality. Questions? Now, of course, a vector from A to B would be a space-like vector. A vector from A to C would be a time-like vector. And on the light cone, it's called D, the vector from A to D would be a null. Is that clear to everybody?
Can you please repeat about the null vector?
Yeah, the null vectors, right, are vectors whose norm is exactly equal to 0. Okay, I'll say that in a few minutes. We're going over to go through massless particles.
Okay, thank you.
Okay, that's because the interval for a photon is always 0. Right? Remember the interval? Okay, I'll go back to that in a few minutes. Any more questions?
Yes. So
yes.
What's the meaning of the vector from A to B if it's not physically reachable, it's not causal? What should it say?
Well, it has a mathematical meaning. It doesn't have a physical meaning. Indeed, in this course, we will not be dealing with that. I mean, basically, okay, I should be careful what I say. There are hypothetical particles. You know, if you can think of hypothetical particles that might exist that can travel faster than the speed of light, then for them, they can reach from point A to point B, right? Now, physically, we do not have any evidence for the existence of such particles, right? But if you can think of extension theories, you know, beyond general relativity, you can think of some, you know, you might have heard the names tachyons, or some hypothetical particles that may exist that travel faster than light. Okay? Again, we do not have any observational evidence that any such particles exist in nature. But, you know, theory can go beyond what is currently known. That's one thing. The other thing that I mentioned, if and when you will study quantum field theory, in quantum field theory, again, I'm not going to go into that, but obviously, as you can understand, a lot of the language that we're using is the same language that is used in quantum field theory, because this is a language of modern physics. And there, essentially, the idea is that the universe is filled with fields, right, which are quantized. And in principle, you can have, it's the same problem that you can have a field that exists everywhere. So if it exists everywhere, in principle, it can exist both in points A and B, and it may be somewhat connected. Now, of course, in order to go back to physics, in quantum field theory, there is a clever way of canceling the integrals such that everything which is beyond the light cone gives you 0. If and when I'll teach you one day quantum field theory, we'll go into that in depth. But right now, this is not my task. So just that you know that it exists. And then if you go and learn quantum field theory, is normally learned in a master's degree. It is not learned in as an undergrad, and there is a reason for that, of course. You need to know quantum mechanics first. But if and when, then you should know, you should pay attention to this point because this point does exist there. Okay, so for us, it's important for me that you understand the definitions and understand what they mean. Physically, every massive particle, right? So myself, for example, my world line always has to be within the light cone. I do not, as being an object with a mass, myself and yourself and everyone, you do not have the possibility of traveling faster than the speed of light, and you do not even have the possibility of traveling at the speed of light. But from a physical point of view, you do have the possibility to travel everything within the light cone. That you can do. It's just a matter of engineering, building the right machine, building the right engine that will take you there. Of course, the engines that we managed to build so far, the fastest ones go very, much less than the speed of light, right? So the real world line that we have looks something which really looks like that, right? We don't really have a way of traveling even remotely close to the speed of light, but it doesn't matter. It's just for the sake of understanding the basic concept. Okay. Any more questions about that? No, okay, good. It's still the recap of what we did last time. So I said, okay, so the way to describe the location of something, right, is to say, okay, this something is looking at the world line of this something, which could be my world line, the world line of a particle in an experiment, the world line of anything. And then I just quantify the location along the world line. Right, so I'm just taking this path. You can think of it as a rope that you're putting, in your room, like a kid's game. So you put a rope, and you just have to go along the rope, and the rope can take you from one place to the other. And you're always on that rope somewhere, and you want to tell somebody where I am, so you just have to specify some parameter, which I just call lambda. And here is lambda equal to 0, 1, 2, 3, 4, 5, 6, right? This is my parameter lambda. So if I want to say where you are, I'm on the world line with lambda equal to 6. So I'm here right now. I fully specified where I am because it's basically a 1D location. I just tell you how much you have to go along that. Remember that because we'll go through that after the holiday. We'll discuss some more about this concept. Okay. Now we can choose any parameter lambda that we want because it's just a parameter that tells us that how far along the world line we are. But in practice, it's useful to use as parameter lambda the proper time, tau, which can be done as long as the particle is massive, right? Which means that the world line is being specified by the coordinate x mu as a function of tau, right? Yeah? Yes, no, maybe? No? Yes? That should be quite simple. I think it should be quite simple. I don't know.
Yes, it's fine.
Yes, okay, fine, good. So now that we understand that, then the generalization, we get the entire special relativity that you've seen in first year basically for free, right? Because now we can define the 4 velocity, right? u mu is just defined to be dx mu over d tau. Right? That's the definition of the forward velocity. Right? Remember, delta tau squared was defined to be minus 1 over c squared eta mu nu delta x mu delta x mu. Right? So from that, we get that d tau is just dt times square root of 1 minus beta squared, which is just dt over gamma. And from that, you immediately get that u0 is just, in real units, right, it's just gamma c, and ui is just gamma beta I c, right? Beta I is just the normalized velocity in the ith direction. Which again, of course, generalizes immediately to, reduces, sorry, not generalizes, reduces immediately to the familiar velocity, because in the limit where everything is non-relativistic, because when everything is non-relativistic, right, gamma is just 1. Beta is very, very small, gamma is just 1. So beta times c is just vi. Right, so in the non-relativistic limits, this is just c and this is just vi. Right, and an interesting feature is that the norm of u, right, u squared, u mu is a constant. It's minus c squared, which we showed. Right? And the next is also pretty much straightforward, just defining the forward acceleration. A mu is defined to be du mu over d tau. Again, right, this is the forward acceleration. And of course, the forward force, F mu, is just m a mu. And I showed you an interesting result, which seems to be a bit confusing at the beginning, which is that a mu, u mu is just 0, which means that the two vectors, the forward acceleration and the forward velocity, are orthogonal to each other. This may sound a bit confusing, but when you think of it, there is nothing really unique here. It just tells you, we have here a summation of 4 terms, right? It just says that the one of the terms, which is the 0 term, is just dependent on the other 3 equations. That's it. So if you see that, don't get, sometimes when you work with 4 vectors, especially when you're not used to it, you get some results which look really strange at the beginning. But then when you think of it, then you end up that, oh, actually, just a mathematical thing. There's nothing really physically interesting or unexpected happening here. And then after that, we said that the generalization, again, continue to generalize. After defining the forward velocity, then the next thing we defined was the forward momentum. Just m dx mu over d tau, which is just m u mu. This is a definition of the forward momentum. And then from what we got here, it's quite straightforward, right? It's done nothing to do really. P0 is just gamma MC, and Pi is just gamma beta I MC. But now comes the trick, right? Because now when we look at the non-relativistic limit, And now we take the first expansion in a Taylor series. We end up that P0 is equal to MC plus 1/2 mv squared over C. And Pi is just mvi. So Pi we identify as the momentum. And P0, when we multiply by C, we got that it's mc squared plus 1/2 mv squared. And here comes, this is the amazing thing that Einstein got, right? That the second term is immediately identified as the kinetic energy of a particle. There are some higher order corrections. Square or even cube, I think. I'm not sure if it's a square of a cube. You can check it out. I think it's a cube, right? So this is identified as the kinetic energy. But again, this just comes out immediately out of the equations. This is something which has units of energy, and Einstein identified it as the rest mass energy, or the energy associated with the mass of any massive particle, right? But the truly amazing thing is that it just came out right of the equation without needing to do anything. You didn't even have to think of it. You just have to look at the equation and say, hey, what do I see here? And of course, that's huge, right? Because C is much greater than V in this non-relativistic limit, which is huge. Of course, the correct amount of energy is gamma times mc squared. Right? So if we have a particle that moves relativistically, it has a huge amount of energy because gamma can be arbitrarily high. All right. And then again, we ended up with just small algebra, give us again at P0, which is E over C, it's just Pi squared plus m squared C squared to the power 1/2, which is again something which you've seen in your first year. And here, hopefully, you can see that again you get this just using the formalism right away. There's nothing much. There's nothing really that you have to do. Any questions? No, it's all clear. Okay, so let's go back to the question that I was asked. Basically, completeness. There are small things to complete here. So I'll see how much it's going to take us. I may do a small tutorial, I may not. Depends on how much time we have and how fast we go. So massless particles. Namely photons. If one could quantize gravity one day and end up with a graviton, then you could also have graviton. Right now, we only have photons. Neutrinos, we know today, are nearly massless. They are very close to being massless. They have very, very small mass, but they do have some mass. So right now, we can think of photons, which is the most important example that we have. Right now, a photon always travels at the speed of light, right? So if a photon travels at the x direction, then obviously x is always equal to ct, right? What does it mean about the proper time? We already said it. What is the proper time?
0.
0, right? So delta tau for a photon is always 0, which again, it's kind of surprising if it's the first time you think of it, right? From the photon point of view, from the time it was emitted by some process in the sun to the time it was absorbed, say by your eye or by anything else, it took 0 time. It had no time, right? So we cannot really use the parameter tau to specify where we are along the world line of a photon, right? This would be the world line of a photon here. Right? So I cannot use tau because delta tau is always 0. But again, I'm not concerned too much because I simply choose another parameter which I arbitrarily called lambda. Again, right? So I just call it lambda. What is that? For the time being, I don't really need that. I don't really need to specify what is exactly lambda. I just know it is there. Right. And then if I want to specify a 4 velocity for the photon, it always has to be u photon 4 velocity. I'll have to write it down as u mu is dx mu over the lambda. Right. But of course, I know it's a null vector because the interval is always 0. Right. So it's a null vector. So that means that u squared is always 0. So that's also why I don't really care about the exact value of lambda, right? And I'm not saying anything new. I'm just saying it in the same formalism that we're using. That's it. So just really to show you that the formalism can work for massless particles as well, right? And if there is no force, right, an equation of motion, it's going to be du over the lambda is equal to 0, right? The photon continues to travel at the same speed, which is what it says, right? In the absence of force. About the energy, right? Einstein showed that the energy of a photon, right, is related to the frequency of the photon, right? E is just h bar omega. Again, this is Einstein's equation, right? H bar is Planck's constant. Photons do carry energy, but these are related to their frequency, right? And then we can use this equation here. Of course, the mass of the photon is 0, so we can relate pi, the momentum, right? Pi is just E over C, right? Which is written as h bar k, right? K, of course, is the wave vector of the photon. So if we have to write down the form momentum of a photon, it's going to be h bar omega over C and h bar k. Which I believe you've seen it, right? I mean, you know what is the energy of a photon. You've seen that in, I don't know if in modern physics, right? And of course, using this relation, right, it's kind of automatic to show that p squared, what is p squared? For a photon? Yep, I'm waiting. What is p squared of a photon?
0?
0, of course. Okay, again, it may look a bit confusing, but really really it's not. Again, what I suggest right now, you're going to pass over holiday, right? Go back to your first year relativity. You learn it in course of modern physics or modern, I don't know what course is being taught here. And look at that. It's the same. I'm telling you everything you know. I'm just telling you in the general mathematical formalism, right? Or language, which puts everything in a very simple and structured way. Okay? Believe me, it's the same. And so just get used to the language, and you're going to use that because we're going to use this language from here to come. And also, I kind of hinted to you, the same language is used in several branches of modern physics, not just relativity or astrophysics, but also in quantum field theory, string theory. A lot of these theory things use the same language. So if you know it, it's basically it's modern 20th century physics. I've even seen that in optics, actually, though I'm not doing optics myself. Okay, so now for something which is maybe new, maybe not, and we need that. So far we discussed the motion of a single particle, right? Which is fine. You know, when you make experiment in CERN, we talk about single particles, right? But in reality and in astrophysics, in general, we often encounter systems that have many particles, right? So many particle system. Right. Many particles that behave collectively somehow. How do we call many particles that behave collectively? You know, we can specify their properties by some, you know, in some collective way.
Fluid.
Fluid, right? Fluid, gas, right? And we have that, right? In astrophysics, we have that all the time. And we're going to use that. So many particle system. And the way to specify is called the energy and momentum tensor. Now, energy momentum tensor is something which you might have encountered in your advanced E&M course, electromagnetism. Another name for that is the stress energy tensor. Have you seen that in your electromagnetism course, or possibly any other course if you studied in fluid course, I don't know. Have you seen that before? Well, somebody has to answer me when I'm asking. You can say no, no shame.
Either no, or maybe I didn't pay attention, but anyway, I don't remember it.
Didn't pay attention, okay. No, because the question, is there anybody who claimed that you have seen that? No, nobody? Okay, I don't know what people teach you in the advanced E&M course. I think I've seen that in the advanced E&M course. Of course, the question is if you've seen that as did you ask the definition for a tensor? But anyway, it doesn't matter. So we're going to show it right now. The reason why I ask you that, why I tell you all these stories, because this is not something which is only seen in general relativity. It's something which is, again, quite common in modern physics. Okay, so as we said, right, for single particle, when we have a single particle, it's enough to specify the form momentum that will tell us anything we need to know about it. For extended systems, we have to define the energy momentum tensor. So energy momentum tensor, I do a little bit of hand waving in defining it. It's only a little bit, not too much. Simply because I don't know what's the simplest way of defining it. Energy momentum tensor is often defined as T with two upper indices, T mu nu. Again, you might have seen that, or you will see it in the future in either electromagnetism, fluid dynamics, or solid states, that you might see it as well. So this is a symmetric tensor. It's a 2-0 tensor. This is a symmetric 2-0 tensor, right? Tensor of rank 2-0, which basically tells us everything we need to know about the energy or energy-like aspects of the system at hand, which involve the energy density, pressure, stress, temperature, everything you want. So intuitively, right, T mu nu, has 4x4 matrix, right? Then it's the flux of the 4 momentum P mu across a surface of constant x nu, right? So if you think of it in terms of fluids, right? So let's say that we have a fluid, right? We have a stream. So I take a box, right? So there is some motion in this direction, but I might also have some motion in that direction as well, right? The fluid, maybe some turbulence or some motion in that direction, right? So the nu component, right, will tell me about the flux of the 4 momentum. So let's say this would be x1 and this would be x2, right? So I may have some fluid element which also has some momentum in the x2 direction, which crosses a boundary, right? So there will be some 2-1 component of that matrix, right? There's a P mu momentum that cross the x1 boundary. Okay, you with me? I think the easiest, when you get confused, think of a river. There is a river, there is some flow, and then there is some eddies, some turbulence. The water is not just flowing straight. It's not just a pipe. It's a river. So things happen. Okay. Right. So the T mu nu. T mu nu intuitively. Right. T mu nu is the flux of 4 momentum P mu across the surface of constant x mu. That's the intuitive. Right. Now I haven't really defined what is a fluid, right? But when you think of a fluid intuitively, again, it's a continuum of matter that you can describe by a set of macroscopic quantities, right? So a fluid it's a continuum of matter that is described by some macroscopic quantities, right? Temperature, pressure, entropy, viscosity, right? These are all macroscopic, right? You cannot assign a temperature to a single particle. But when you have a collection of particles, right, the air in your room right now, then you can assign a temperature to it. Okay, so this is a statistical mechanics way of describing it, right? So you have temperature, pressure, entropy, viscosity. So in fact, we're not interested in a fluid per se because that's too general. What we're interested in is what's called a perfect fluid. And the nice thing about perfect fluids is that in astrophysics, nearly everything, and when I say everything, I mean everything, is a perfect fluid, right? plasma inside the sun is a perfect fluid. The electromagnetic field is a perfect fluid. The entire universe is a perfect fluid. Okay? In astrophysics, everything is a perfect fluid. So what is the difference between a fluid and a perfect fluid? Well, there are several definitions. So I went through the textbooks, and I encourage you to go through. For example, the textbook by Schutz that I pointed out argues that, defines the perfect fluid to be one with no heat conduction and no viscosity, right? So a fluid that has no heat conduction, no viscosity. The other textbook by Weinberg defines it as a fluid which is looks isotropic in its rest frame. Let me use this definition, right? Is a fluid that looks isotropic in its rest frame. Right now, actually, it can be proven that this is equivalent to the other definition of Schutz: no heat conductivity and no viscosity. For our purpose, that means that we can completely specify the fluid by only two things, only two numbers, which is the pressure and density. Fully specified by pressure and density. All right. So, questions? No? If not, then I can now define the stress energy tensor. But even before that, let me start with an even simpler fluid, which I called dust. So what is a dust? What do I call dust?
It's a fluid without pressure.
Exactly, it's a fluid without pressure, right? Dust is a collection of particles, right, that are at rest with respect to each other. So I have a collection of particles with respect to each other, they are at rest. You have it on your floor, I'm sure. I have it on my floor, right? They're at rest, so that means that there's a zero pressure. So alternatively, you can think of a dust as a perfect fluid with zero pressure. Right? Now, of course, you know, they are at rest with respect to each other. That means that any frame, they all have the same velocity, right? If you're in their rest frame, you see them not moving. But if you're in any other frame, you might be seeing all of them moving with the same velocity, right? So you can think of a four velocity field, all particles have the same velocity. Right, so we can think of a four velocity field. U mu of x, which is defined everywhere, because there's dust everywhere, right? So now we can define the number flux flow vector. Right? And mu, it's a 4 vector, which is n times u mu. And of course is the number density of the particles as measured in their rest frame. Okay, but this is in the rest frame. Now, what about the general frame? Right? So arbitrary frame. Then what would be N0? Right? Now, arbitrary frame, the particles are moving, or seem to be moving. All of them moving together at the same speed, same velocity. Right? So N0 is the number density, and Ni would be the flux of particles in the I direction. Right? N0 would just be the number density. And I would just be the flux of particles in the xi direction. Right? Of course, in the frame in which they are at rest, right, in the rest frame, what is the number flux for vector? Right, what is N mu? When the particles are at rest, what is the zeroth component of N? N mu? N, small n, right? And what's the ith component?
0.
0, right? You all see that? When the particles are at rest, then all the ith component of U are 0. Because it's not moving anywhere. The zeroth component of U is just 1. So you need exercise, huh? Yeah, okay, you got one. I can give you the second one, but I can wait until the end of Passover. Okay, right? Now, let's say that each particle has, let's say all the particles have the same mass, right? And the same mass m. Then what is the energy density in the rest frame? What is the energy density in the particles rest frame? The particles are not moving.
How it is defined? It's like N mu, N nu?
No, what is the energy density?
MC squared mu.
Sorry?
MC squared mu.
Very good, right? It's rho, it's just n times mc squared. I have to tell you that when I was a student, I also got confused by the idea of an energy density. I'm not sure why, now when I think of it. Because I can understand the concept of, intuitively, the concept of number density. It's just the number of particles per unit volume, right? I have 10 particles per centimeter cube. So the number density of particles is 10 per centimeter cube, right? But now I can say, okay, what is the energy density? It's just the total energy that exists per centimeter cube, right? Now these particles are at rest. So each particle, the energy that it has is mc squared. If it has mass m, it's not moving anywhere, right? And the density of particles is n. So total energy density is just n times mc squared. I don't know, ergs or joules or whatever you want. I like ergs. Well, in astrophysics, we do CGS. I think Ofek told you that, right? So ergs per centimeter cube. And there's nothing really fancy here. Nothing that should make you feel bad. Okay. Now, so basically this energy density is completely specifies the dust, right? That's all the dust is. But of course, rho is the energy density in the rest frame. If you want to have something general, you want to have something that is true in every frame. So how do we generalize this concept to any frame? So what about any frame, right? So here comes a bit of a hand waving, but really a bit, right? So when we look at the energy density, we see that it composed of two separate entities. There is the number density, and there is the energy per particle, n times mc squared, right? Now, both of them are really the zeros component of a 4 vector, right? So, in the rest frame. So, we said that n mu is n times 0, 0, 0, right? So it's the zeros component. And of course, what is mc squared? It's a zeros component of what?
For moment.
Of the 4 momentum, right? So p mu is just mc 0, 0, 0, right? So that enables us to think of rho to be the 0, 0 component of a general tensor, right? As it is being measured in the dust rest frame, right? So that enables us to define T mu nu dust as P mu and nu. This really would be the definition here, which again is N M U mu U nu, or rho U mu U nu. C is equal to 1 anyway. It's always equal to 1, except in your exam, of course. Okay, and what is, of course, the energy density in the rest frame? Okay. Now, by the way, you may not be familiar with that, but right, this enables a very elegant way of writing conservation of particle number. There's many elegant ways here that you will get familiar with when you start working with this, right? But for example, conservation of particle number, I can write using the gradient. Right? D mu and mu equal to 0, that's all. That's how I write conservation of particle number in a modern form. It's called covariant form. Now remember, when we use U0 is just gamma C and UR is just gamma beta IC, right? What's written here, D mu and mu, again, there is a summation here over mu, right? So D0 and 0, right? Is just D gamma n over dt plus D mu is equal to I, right? So D over dx of gamma n p is equal to 0. If the second term is not familiar to you, it's just a gradient, right? Of course, in the limit where gamma goes to 1, you get back to the classical equation of conservation. By the way, did you ever see the equation of conservation? Or this is the first time that you're seeing it? How many of you saw the conservation equation of particle number? Oh no. Maybe completely out of focus. How many of you have seen the equation of conservation of particle number?
I've seen it, I don't know.
Flow of a river.
זה חוק הרציפות.
You take a box inside the river, right? The flux of particles, the change in the number of particles inside the box, dn dt, is equal to what? To the flux of particles that get inward minus the flux of particles that get outward. Right? Now the flux of particles that get inward minus the flux of particles that get outward is exactly the gradient of flow, right? The flow is n times v, right? Minus d over dx of n times v dx. Yeah. It's 1d. If I multiply that by, if each particle here carries a charge, right, q, what do I get? These particles are electrons. What do I get?
Continuity or
Conservation of charge. That's kind of fun. It's all the same equations. But okay, if you've never seen fluid dynamics, then I may be going one step too much. Okay, well, that's basically fluid dynamics, and this is the general, this is the relativistic version of it, which is written in an extremely nice and compact form. And of course, it reduces to the fluid equations. Okay, so this is about dust. Yes.
Sorry, I have a very stupid question. I'm a little bit confused with that definition of gradient. This looks to me a different definition than the classical definition of gradient that we have. So for me, a definition of gradient is something that takes a scalar and makes it a vector. It's always something that goes +1 in dimension. I'm just getting a little bit confused by this definition. I can very well live with this definition. There is not a problem, but
this is definitely the definition. We spoke about gradients last time, right? Gradient of a vector. Sorry, gradient of a scalar. Okay, here's what confuses you. A gradient of a scalar, right? We said it's actually a dual vector, right? A gradient is actually a dual vector. That's what confuses you, right? We discussed that a while ago. D phi over dx.
Yes, so it's another definition as the classical definition.
This is the correct. This is the general definition. The classical definition would reduce to it.
So if for instance, if you take the classical fluid mechanics equation, right? Yeah. Then you would write, so it's dn over dt plus v vector scalar gradient rho, right? So this gradient here, so the one that people are calling gradient, or it's actually something that goes from R to Rn.
Right,
It's
but-
just a matter of definition of gradient, I think.
Right. No, you're right. You're right. It is confusing, but again, the solution is to remember that the gradient is not a real vector. It's a covector. When you think of it in terms of a covector, everything makes sense.
Okay, I will work this out then. Okay, thanks.
Okay, work this out. And indeed, we'll discuss that further on a few weeks' time. I won't leave it like that, but yes, go and review it. Remember that this makes everything works out perfectly fine when you remember that a gradient is a covector, is not a vector.
Yes, I also have a question.
Yeah.
So the energy density, the energy momentum tensor that you define, it's like an educated guess that you said, okay, it's P mu and nu because it makes sense in some sense, so let's use it. And this is the definition.
It's a bit more than that because I said, okay, I know what is the energy density in the rest frame, but now I'm asking what would be the energy density in an arbitrary frame. I want to be in any frame. So it's not exactly an educated guess. I just noticed that the energy density is composed of a multiplication of two objects or ingredients, which each one of them is the zeros component of a 4 vector. Now, when I want to go from one frame to another, I know how to take a 4 vector from one frame to another, right? So I want to be fully consistent with the mathematical structure that I develop. I don't just take a quantity by itself and I say, oh, in general frame, it will look like that. I'm using the same transformation. I say, okay, I know how to transform vectors. This is what I know, right? From one frame to the other. And I know that this looks like a 0, 0's component of a vector. And I know that in this particular frame, the rest frame, all the other components of all of these vectors would give me zeros, right? So this is a general way which will ensure that I know that I have the right Lorentz transformation, and I know that I reduce to the correct answer in the rest frame.
So you also want to keep everything to be a tensor, just so you can play with it nicely.
Yeah. Oh yeah, that's crucial. Because I know the transformation laws of vectors and of tensors. I don't know the transformation laws of other quantities. In fact, everything I'm going to do, and you'll see that, and that's going to be crucial. We'll discuss that immediately after the holiday. I only want to work with vectors and tensors because this is the only thing that I know how to transform properly from one frame to the other without making a mess.
Okay, thanks.
So it's not just a guess, wise guess. It's I want to stay within the structure the mathematical structure that I built. Okay. More? Okay. So now let's go. This was dust. Now I believe you're all mastering dust. This was a very, very good question. It was a very important question. Okay, everything I do here, I don't just do a wise guesses. I enforce myself to stay within the mathematical structure that I put in. It's crucial, otherwise you get lost. I mean, you can get lost within the mathematical structure, but then you just follow the math and it will take you out of your lost place to a place where you're not lost anymore. Okay, now fluids. So dust is great, but we said that dust doesn't have any pressure. It's a 0 pressure, but in reality, there is a pressure. So when we say perfect, okay, perfect fluids. Let's say perfect fluids, that means that there is a isotropic in the rest frame, right? Right. Now, which means if there is a isotropic, what can I say about T mu nu? If it is isotropic?
Symmetric?
Even more than that. Symmetric, I said originally it has to be symmetric, but even more than that, has to be something which is even stronger than symmetric.
Diagonal.
What? Diagonal. Who said that?
Diagonal.
Very good. It's diagonal. That's right. It has to be diagonal, right? Because we said that any off-diagonal term, right, means that there is some flow of momentum, right, in some direction which is orthogonal. And we don't have that because it's isotropic. That means the T mu is diagonal. Right? So no net flux of any momentum in any orthogonal component. So also, because it is isotropic, that means that all the space-like components must all be equal. There is no preferred direction. Right? No net flux of momentum in orthogonal direction. And also T11 must be equal to T22, must be equal to T33, right? So really we only have two independent components or numbers, right? So only two independent ones will be T00 and TII. Right? So we can say, okay, T00 would be rho, because we know this is the case in dust, so we can put TII to be the pressure. Let's say this is a guess, right? Now, so we may think, so in the rest frame, right? We may have that T mu nu would look like a rho P, 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 and then everything else is zeros. Okay. This makes sense, right? It reduces back to the energy momentum tensor in the dust, for dust, zero pressure, right? But what about any frame, right? Which is not addressed. So generalize, right? Right, so for dust, right, we wrote down T mu nu as rho u mu u nu, right? So we can guess that T mu nu would be rho plus P times u mu u nu. But of course, if we do that, then of course this gives rho plus P in the rest frame, right? And then everything else would be zeros. So that's obviously not what we want. We want this to be in the rest frame. So we must add something. So let's add. What do we need to add? Oh, that's really simple. What do we need to add to our wise guess to get back what looks like a reasonable stress energy tensor in the rest frame?
Matrix multiplied by P.
Excellent. Minus P plus P plus P plus P. Right, which is just eta mu nu times P. And that means that the general way of defining the stress energy tensor or the energy momentum tensor, right, is just P or rho plus P u mu u nu plus P eta mu nu. Okay. This is a tensorial identity. We have tensors, both sides. Right? That's the definition of T mu nu. I'm not just wasting your time here, right? We're going to use this formula, of course, especially it's very useful when we speak about stellar dynamics. It's very useful when we speak about cosmology, about the evolution of the universe. Okay, so I wanted to introduce this formula, right? It's called a covariant form of the formula. Okay. Fine. One important property, right? So it's symmetric, right? It's obviously symmetric. You can see it right away just from the structure, right? Symmetric, if I change T mu and nu, right? T mu nu is equal to T nu mu, right? That's obvious. That's symmetric. You can see it from here immediately, right? You change mu and nu, right? Mu and nu you can change, or mu and nu change, and then nothing happens. The other thing, again, since you haven't seen fluids, then the other important thing is it's conserved. And the way to express conservation, right, is vanishing of the divergence. So the way I'm going to write it, again, in a very compact form, is just d mu T mu nu equal to 0. That's a conservation. Conservation of T mu nu. That ends up with an Euler equation, which is equation of motion for fluids. Now, again, if you haven't studied that in fluids or haven't seen it, there's no point that we'll discuss it any further. Because it's not, we're not going to, except from that we're going to use this formula actually. Again, we have here sum over mu, right? So nu equal to 0 is a conservation of energy. And nu equal to I, right? This is what? Any guess?
Conservation of momentum.
Yeah, exactly. This is conservation of the I component of P. Okay. Okay, that's a very important property of T mu nu, which we will use in the future. Just that you know it. Again, it takes time to practice it, that you see. Any questions? Any questions? No. Okay, so we have something like 10 minutes. I thought of, I wasn't sure how long it was going to take us. There were two things which I thought of putting in. One is sort of a tutorial about vectors and coordinate change, but that's not going to be 10 minutes. And I want to see if it's needed or not, because I'm not sure that it won't confuse you. It could be more than an hour. Another thing which is kind of fun is the covariant form of Maxwell's equations. We're not going to use it really in this course because we're not going to do electrodynamics, but I think it's kind of fun to see and sort of for completeness. So, and I think we can do it in something like 10 minutes or so. So I think we can do it now. So let's look at the modern version of Maxwell's equations. Now you've all seen Maxwell's equations, right? Yeah, you must be. Do you want to help me with them? Or should I trust that you know them? I should trust you, huh? Okay. So 19th century language, right? Nabla cross B, right? Minus dE dt is 4 pi j, right? Nabla dot E is nabla dot E is?
Over epsilon
By
0.
rho.
I'm using MKS actually. Okay, 4 pi rho, right? C just to means the charge density, right? Nabla cross E, right? Plus dB over dt is 0, and nabla dot B is 0. These are Maxwell's equations. You've all seen them. Now this is the 19th century formalism, 19th century way, right? E and B, there are 3 vectors. Now there is a modern language to write them, right? So, you know, the curl and the divergence, right? You've all seen that. Now, as we said at the beginning, right, these equations are invariant under Lorentz transformation. Right? In fact, that's the original way that Lorentz transformation, that's the original reason why Lorentz transformation was invented, right? So, that means that we can write them down in a very compact form, pretty much like we wrote down this stress energy tensor, right? You with me on that? Or not? We're very quiet. Guys, I want to remind you, ask questions. There is something you don't understand. If you don't understand my handwriting, if you don't understand my English, if you don't understand anything I say or anything I write, it's your responsibility, guys. It is your responsibility. Don't get mistaken. I'm doing my best that you understand, but if you don't understand something and you don't ask, you're responsible that you understand, not me. And remember what I told you, if you don't understand something, you are not the only one that doesn't understand it. Don't make this mistake. Okay, so I want to write down these equations in a compact form. How am I going to do that? That's kind of fun. So the cross term, you might have seen that, right? I can write it down as epsilon ijk dj bk, right? And this term is minus d0 e I. Just switching up upper and lower indices. That is 4 pi ji. Then the divergence term, nabla dot e. How do I write the divergence term? This is just di ei, right? It's just 4 pi rho. I put sorry, I'm gonna write it down. Okay, 4 pi j0. Where I just define the current 4 vector. But let's write down the other one. So the other 2 equations are epsilon I j k dj ek plus d0 bi equal to 0, and the last one is di equal to 0. Right? Now I can raise the lower indices as I want because it's all 3D, and in 3D, you know, eta is just the ones. So I can use the delta function to raise and lower. It doesn't care. I don't care. And the epsilon is the Levi-Civita, right? The three-dimension version of the Levi-Civita, right? When I define the current 4 vector, right? J mu is just rho charge, right? J1, J2, J3. Right, just the density and the flux in one vector multiplied by the charge. That's it. Right? The current is just the flux of charges. Hey, admit that it's cool. Don't see happy faces. So now the trick is to define the electromagnetic field strength tensor. The real way of defining it is using the potential, right? We can write B as a curl of a potential, right? A. So really, F mu nu would be just be D mu A nu minus D nu A nu. Should be the definition, but I haven't defined what is A. So let's, instead of that, I'll just write down F mu nu is just 0 and then minus E1 minus E2 minus E3, E1, E2, E3, and then 0 on the diagonal, and then B3 minus B2 and B1, E3, B2, and minus B1. So it's an anti-symmetric tensor. That's called the electromagnetic field stress tensor, and the reason why it's denoted with an F is in honor of Faraday. So that's called the Faraday tensor. Okay, this is for advanced. You see, read, Google it, see why I wrote it like that. That's a definition. Some textbooks have some minus sign, which makes my life miserable. I think Jackson actually uses the opposite sign. I'm not sure, but that again goes back to the fact that in particle physics, the eta mu nu is defined with a minus sign, the one that we're using. That's the one that I'm using, so that's fine. So what is F0i? What is F0i?
Electric field?
Yeah, right. So I'm going to use with an upper indices. F0i is just EI. What is Fij? F12. What is F12? What is F1? What? It's B3, right? So it's epsilon ijk bk. You all remember the Levi-Civita tensor, right? Just give me the sign. So with these definitions, I have these two equations, which I can write down. djfij minus d0f0i is 4 pi ji, and dif0i is 4 pi j0. But d0f0i, f is anti-symmetric, so it's a plus d0fi0. So when I merge them together, I end up with d mu f nu mu equal 4 pi j nu. These are the Maxwell's equations. Two Maxwell's equations. This is the compact form of Maxwell's equations. It contains exactly the same information as the informations that these two equations have. Just written in a very compact form. Cool, isn't it? What about the other two? Okay, there are various ways of showing that. And I'm leaving up to you. I'll just tell you what the answer is. The other two equations can be written as d mu f nu lambda equal to 0. So this is the first and second. It is the third and fourth Maxwell. But I have to take here the anti-symmetrization. So just that you know, this is actually good that we have it because we might use it in the future, the anti-symmetrization. So this symbol, the square bracket symbol here, it's an anti-symmetrization of the indices. Right? So that means that we're summing over all possible permutations like we do with the Levi-Civita, but we're reversing the sign for any odd permutations, right? So just to get the feeling, right? So if I write down T mu nu rho sigma and I take the anti-symmetrization, that means 1/6 of T mu nu rho sigma. Now the sigma I don't touch because it's not part of the it's not within the brackets. But then when I start to switching, right? So it will be minus T mu rho nu sigma, right? Plus the I can switch it to be rho mu nu sigma minus T nu. What did I do here? Mu rho sigma plus T mu rho mu sigma minus T rho mu sigma. Right, the 1/6 is for normalization. I'm not going to prove this to you. This is an exercise. You can look at it at home. So this is also the Maxwell's equations. This is the modern form of Maxwell's equations. Now, the important, well, there are many important things here, but one thing which you can clearly see is that this is a tensorial equations, right? That means that these equations transform as tensors, which means that if they are true in one frame, they are true in all frames, right? So, and that makes these things very useful, right? Because once you have something that you know how to transform from one frame to another, then you're good to go. This is called the covariant form of Maxwell's equations. Covariant form of equations. Covariant means that they're written in such a way that they can automatically know how to transform them from one equation to the other, from one frame to the other. I gave you a small example, right? That you see the strength of that. We'll discuss that in depth after the holiday, right? When you write things in a covariant form, then you automatically get the transformation laws of them. For example, right? If I take the determinant of f, right? This is a scalar, right? So the determinant of f, if you go back to the definition here and you calculate the determinant, this is just E dot B squared. Since this is a scalar, that means it's going to be scalar in any frame. So from that, we automatically get that in any frame that you look at, E dot B is fixed, regardless of the frame. You don't need to do anything. I don't know if you've seen an E&M transformation of fields, electric field and magnetic field. Did you see that in any of your advanced E&M courses? Yes? It all comes from here. You can get everything you've seen there, you can get from here at 0 time. and with much less mistakes. Another example, right? Another scalar is f mu nu, f mu nu. This is a scalar, of course. When you calculate what it is, it's 2 times sum over I, bi squared minus ci squared, if I'm not mistaken. But again, that means that b squared minus e squared is conserved quantity. B prime squared minus e prime squared. Something which is conserved. Does that ring a bell? Oh, I've been going way too far. Okay, let's stop. I went, the last 10 minutes or so were not really necessary because we're not really going to do electromagnetism in this course. We're going to do GR. Okay, stop. We're going now for a holiday. Have a good holiday. Have a productive one. Go back and review the material. Okay, you're going to need it. Trust me, you're going to need it. Everything we said up until the last 10, 15 minutes where we spoke about the electromagnetism are things that we're going to need. It's not really difficult. It's just a structure. Again, what did we do? I defined the Lorentz transformation. I defined a 4-vector. I defined the Lorentz transformation, right? Then I defined 4 vectors in general, right? And then what did I do? Right? I defined, we defined the interval, defined Lorentz transformation. We defined 4 vectors. We defined, we discussed the basis vectors versus the 4 vectors, right? We defined the covectors, we defined tensors, and then everything we did in about the physics can be summarized in these few pages, which we did earlier here, right? Just defined the word line, for velocity, for acceleration, for momentum, and that's pretty much it, what you need to know. And then we discussed the stress energy tensor. I did my best to give you some feeling of what it is really. Okay, that's it. The mathematical structure is the important thing here, because everything that we're going to build will be built on that structure. Okay, and the amazing thing, to my point of view, is that the physics just follow immediately. Once you accept the structure, everything just follows. You get E equal mc squared for nothing. You just, just there in the equation, and you just have to see, oh, what does it mean? That's all. Okay.
Thank you.
We're done. Sorry?
Thank you.
Okay. Enjoy your Passover holiday. If you have any questions about the homework are due by the end of this week. So basically by Leila Seder. Next problem set, I wait until the end of the holiday to post them. It will also deal mainly with special relativity. Review the, use the time. Review the material, make sure that everything sits properly in your head. Because things will get more confusing down the line. See you guys. Thank you very much.
Bye.
Thank you. Bye-bye.
Sharing, I can do recording.